Well, good afternoon. This is 12:22 on Monday, the 6th of November, 2017. This is supposed to be Calculus 3 class, Math 227, but right now I'm the only one in the room. Hopefully some of the others will be coming in soon. Let me get started from the current slide. There are just a couple of announcements I do need to make today. First, as far as I know, there's no office hours changes for me this week except on Friday. And this will affect all of you because Friday is the 10th, Saturday the 11th is Veterans Day. The state of Alabama tends to take Veterans Day off pretty much across the board. Maybe not everybody, but a lot of people do. The state government does anyway. So there will be school will be closed on Friday. I will not have any office hours. I will not be on the Birmingham campus or Bessemer campus on Friday from 7:45 to 11:45 when I usually am. So don't come by. The school is closed. Now, other thing I wanted to remind you of, I know there's only a few of you in the class, and I just realized I forgot to mark roll in this morning's class. Let me do that quickly. Okay. But hoping that, all of you appear to be 18 years old or older, and hopefully you are registered to vote. If you are not registered to vote, you still have plenty of time to register. It's by the end of this month sometime, or sometime getting toward the end of the month. But please register because there is an important election coming up on December the 12th. It's Tuesday, December 12th, second Tuesday in December. It's a special election for the Senate race, the seat that was vacated by Jeff Sessions when he became Attorney General. It was appointed by our previous governor, who's no longer there, to his Attorney General, apparently, so the Attorney General wouldn't prosecute him for misdoings. He appointed him the Senate seat. Then the new Attorney General didn't bring the charges, and the governor got out anyway. But he wasn't supposed to appoint somebody. It was supposed to be a special election. When the new governor came in, she said, no, we have to have a special election. So we've had the primaries, we had the runoff in the Republican primary, and now we're ready for the election for that seat. Well, a very important election coming up, December 12th. Please, if you haven't registered to vote, register to vote. If you have, please don't forget to vote on December 12th. Now, I don't know where your local polling station is. If it's somewhere out of town, you can still get your absentee ballot in time. December 12th is close to finals week, but not exactly. It just depends on where you are. But please plan to vote. Please don't miss the opportunity to vote on December 12th. Okay, we're beginning now today on the heat equation, which is at the top of page 763. We're in chapter 14, differentiation of several variables, and the section 14.3 is partial derivatives, and example 11 is the heat equation. Here it is in tiny, tiny, tiny format. That's as much as I can blow it up. It's still pretty sparse. And it says that show that this heat equation, I've got to find my pen here, there it is. That this heat equation, U of X, that this equation, get my pen activated here, okay, that this equation, U of X and T, okay, is equal to 1 over 2 times the square root of pi t, and that t is under the radical, e to the minus x squared over 4t. Okay? Define for t greater than 0, satisfies the heat equation which is listed below. Okay? Now, obviously, it's really small to see, but what we've got to do to see if this qualifies, satisfies that heat equation. Now, I think my temptation here is to do this. Rewrite this ever so slightly as 1/2 times pi t to the negative 1/2 e to the minus x squared over 4t. Okay, I just prefer radicals in exponential notation, and I prefer denominators written as negative exponents, okay, when you're doing integration, okay, I mean differentiation, integration too, but differentiation here. So let's first do the partial with respect to t, partial of u with respect to t, okay. Well, there's a product rule here. The 1/2 is out front. That's going to be there, okay. Now let's deal with the first one. And it doesn't matter to me whether you do first times the derivative of the second or the derivative of the first times the second. Really doesn't matter to me at all. So I'm just going to do the derivative of the first, which would be minus 1/2 pi t to the negative 3/2, okay, times e to the minus x squared over 4t. Now, normally we put a plus here, but I know that it's going to wind up being negative, so I'm going to do the negative sign there because I see it's coming. The first, which is pi t to the negative 1/2, and the derivative of this is e to the minus x squared over 4t, okay, times the derivative with respect to t of that, which would be, and here again, I'm wishing, and that's where the negative sign came from, but let me rewrite this ever so slightly, okay. I want to write that as x squared over 4 t to the minus 1. I know that looks a little weird, but to me it's easier to do that derivative, okay. So the chain rule for this, okay, the x squared over 4 is the coefficient of t to the minus 1/2, okay. Oh man, I did a lot of some yard work over the weekend. My back is so stiff. Oh, and the room's so cold it just makes it stiffer, okay. So what I did, the 1/2 is out front, okay, and then we had derivative of the first times the second, and it was going to be plus the first times the derivative of the second. The derivative of the second is going to have a minus in it there, so I went on and put the minus sign there. And derivative of e to the minus x squared over 4 times t to the minus 1 is a minus, but then you got another minus, okay? So that's going to be a plus here, and then we're going to have, I don't have room to write it, x squared over 4, and we're going to have another t to the minus 2, okay? That's written in a pretty lousy place. Let me change that because that could be confusing. I'll tell you what I'm going to do. I'm going to erase that plus sign too and scrunch it up some. Wound up being a plus because of the plus, a minus, and a minus, so that's a plus. X squared over 4, I can't write, t to the minus 2. Okay. Ooh, what a mess. All right. Now notice that, let's multiply the 1/2 through and see what we get. Or we could take another 1/2 out if we wanted to. Let's multiply it through. Let's say, I'm going to rearrange the terms too. So that'll be an x squared over 8, 1/2 times that, t to the minus 2, pi t to the minus 1/2, e to the minus x squared over 4t. I'm going to write it back like that for now. So that's all of that term, minus 1/4 pi t to the minus 3/2 e to the minus x squared over 4t. Okay, so that's the partial view with respect to t. Boy, I'm cold. I've opened both windows. That's one reason I was a little late getting started. It was so cold in here that it's warmer outside than in, so I went over and opened both windows. And I think it's helping a little bit, but this cold air is blowing right down on top of me. Goodness, my hands are so cold I can hardly handle the stylus here. So let's now do the partial of u with respect to x. Okay? We're going to have to do this twice, so let's do it the first time. And what do we have here? Go back to u, and I'm going to take it in this form here. Okay? Partial of u with respect to x. Well, the minus 1/2 pi t to the minus 1/2 e to the minus x squared over 4t. The first part of that was all the coefficient. Where did I get a minus sign? I don't know. 1/2 pi t to the minus 1/2 e to the minus x squared over 4t. That's, okay, this part is the coefficient. The derivative of exponent is itself times the chain rule, which is going to be a minus 2x over 4t. Well, that would be x over 2t. So this changes that to a minus sign. Okay. Minus x over, and it was going to be 2t, but I already had a half there, so x over 4t. Okay? There's the first derivative partial of u with respect to x. That. Now we got to do the second partial of u with respect to x squared. Okay, now we have another chain rule. Okay, so what I'm going to do is get those coefficients out there, which are, with respect to x, the t's are all coefficients. So that'll be a minus 1 over 4t times the square root of pi t. I may regret doing that, but that's all your constant out front. Okay, now all that's left here, all that's left here is an x times e to the thing. So if we do the first one, it's going to be x times the derivative of the second would be a minus 2x squared, because you had one x there already and you do another one, minus 2x squared over 4t e to the minus x squared over 4t I want to say plus, yeah, except, well, we'll pull the minus out again. So this is going to be a plus derivative of the first, which is going to be a 1 over 4t and I want to go and put this no, sorry. I'm getting lost what part I've already done, which I haven't done. Sorry about that. Okay. The first was your x times derivative of the second. And now it's going to be plus derivative of the first, which is 1 times this. So this is just plus e to the minus x squared over 4t. Okay. That's all the second part of your thing is, product rule. Okay, so let's write these together and see what we get. Or would it be better on the previous one to pull out everything? Yuck. What a messy looking thing we have here. Okay, I'm going to pull out an e to the minus x squared over 4t to go with this. So that'll be a minus 1 over, let's do minus e to the minus x squared over 4t over 4t times square root of pi t times a 1 minus 2x squared over 4 4t, sorry. My throat's going on me. I think it has to do with how cold the room is. I think that's it, because I pulled out the other thing. All right, let's see if we can get the top one to be that simple. Okay. Trying to find what I did here. I did the 1/8 times the x squared over 4 over 4 t to the negative 2 pi t to the minus 1/2 e to the minus x squared 4t minus 1/4 pi t to the minus 3/2 e to the minus, okay. Okay. You know what? I've forgotten to do a pi, I believe. Believe that's true. This is such a pain in the neck. 1 over 2 times pi t to the minus 1/2 e to the minus x squared over 4t. So the 1/2's out in front of everything. Then it's 1/2 pi t to the minus 3/2 pi. I need another pi in there because I forgot to take the chain rule of the inner one. So that's going to have a pi up there. E to the minus that plus the first was the, sorry, pi t to the minus pi halves e to the minus x squared over 4t times derivative with respect to t of that is the minus x squared over 4, and then another minus boy, this is really messy. Let's see what they got. All right. Now they started almost saying the same thing I did. I did pi t to the minus 1/2. They just did 1 over 2 root pi times t to the minus 1/2. So that was the same times that. And they started with the partial with respect to x, and they got partial with respect to x of, that is minus x over 4 the 1 over root pi is down there, and I have a t down there, and they put with their other t, which would be t to the minus 3/2 e to the minus, yeah, that's what they got. And when they take the second partial of that, they get the partial, okay, which is minus 4 root pi t to the minus 3/2, that's what we got, times boy, we have very similar forms. It's just really hard to see the, I've gathered terms differently from what they did. Up above it's minus 4 root pi t to the 3/2 minus 3/2 e to the minus 3/2 plus okay. I think they come out being the same. It's just so many terms there. I really don't think it's probably worthwhile hashing those anymore. especially on the smaller screen as I've got. I have to expand some more, and it's just really hard to do. But I think they turn out the same. Just have to go back and see that. There is a historical perspective here. The heat equation is a special case of which that equation we used was a special case introduced by the French mathematician Jean-Baptiste Joseph Fourier. Young man Fourier was unsure whether to enter the priesthood or pursue mathematics, but he must have been very ambitious. He wrote a letter, "Yesterday was my 21st birthday. At that age, Newton and Pascal had already acquired many claims to immortality. In his 20s, Fourier got so involved in the French Revolution, was imprisoned briefly in 1794 over an incident involving different factions. In 1798, he was summoned along with more than 150 other scientists to join Napoleon in his unsuccessful campaign in Egypt. Fourier's true impact, however, lay in his mathematical contributions, the heat equation being one of those. Fourier also introduced a striking new technique known as Fourier transform for solving his equation, based on the idea that the periodic function can be expressed as a possibly infinite sum of sines and cosines. So I'll let you finish reading that. But leading mathematicians of the day, including Lagrange, who they don't picture here, and Laplace, who they don't picture here, initially raised objections because this technique was not easy to justify rigorously. Nevertheless, Fourier transform turned out to be one of the most important mathematical discoveries of the 19th century. The web search on the term Fourier transform reveals a vast range of modern applications. Now, that was back in the late 1700s. Okay? In 1855, a German physiologist, Adolf Fick, showed that the heat equation describes not only heat conduction, but also a wide range of diffusion processes, such as osmosis, ion transport. That's why physiologists got involved with it. And the cellular level, motion of pollutants through air or water. So the heat equation became the basic tool in chemistry, molecular biology, and environmental science, where it's often called Fick's second law, okay? Though it had been developed as a heat equation by Fourier, but it was exactly the same form. So in that one little blurb there, here you have 4 people you could write about: Fourier, Lagrange, Laplace, or Fick. Now, Fick was not a mathematician. He was a physiologist, but he did some pretty major applications of that. You have Fourier transforms you could write about. You could write about Fick's second law and how that he came about that. So there's several paper topics right there in that one little blurb. 14.3, they have a summary there, and then they have preliminary questions, which I would normally ask if you wanted to go over these, but no one's here, so I don't know if it's any sense of my going over them. I would say do the preliminary questions, and if you have questions about how to get the answers, bring those to class next time, and we'll hit those together. All right, 4.3 exercises. Do any of the odds 1 through 7. Do either 9 or 11 or both. Do any of the odds 13 to 39, either 41 or 43 or both. Do 45. Do any of the odds 47 through 55. Okay? There's a couple of potential paper topics there. Heat index and wind chill temperature. You would think they'd be somewhat related, but they really are not. One depends on the heat index is how hot it feels like it is based on humidity, and the wind chill factor is how cold it seems to be based on wind speed. But both of those are basically applications of partial differentiation. So if you want to write about either one of those are both terms that you hear everyday type thing. 55 mentions magnetic declination, which is also refers to a type of partial derivatives, if you wanted to pick up on that. Probably a little less you could do there. All right, then that carried us through 55. Then any of the odds 57 to 61. Do 63 if you can. Getting to be a little more of a difficult problem, so don't get too bogged down with it. See what you can do. And then any of the odds 65 to 71. All right, and then after 71, you can do any of the odds 73 through 77. Then 79 and 81 both refer to something we call the Laplace operator, and it's dealing with definition of a combination of partial derivatives. I'll put it that way. I can't think of a better way to do it. Used a lot in harmonic motion type problems, so Laplace operator. So again, you could write on who Laplace was, or how did he develop this operator, or what are applications of it. So like I said, that's 79 and 81. And then the last question there, 83, last odd number, is one of those hyperbolic ones, and that's the Korteweg-de Vries equation. And you're certainly to write on either of those two gentlemen. Except for this reference here, never heard of Korteweg before, but de Vries is a fairly common name in math and physics. So I'll let you decide what you want to do with that. There is just one further insight and challenge. You don't need to do that, but if you're interested, you can. All right, that finishes now. 14.3 finally. So let's go on to 14.4. Finally, it's beginning to warm up just a little in here, but it's still pretty chilly, but it's feeling a lot better than it did because I have the windows open. All right, waiting for 14.4 to open, and it's taking its sweet time. Okay, I think finally it did. So let's do the slideshow from the current slide. All right, in this section we're talking about differentiability and tangent planes, okay? And there's going to be some new kind of ways of looking at things, but then we're going to get back to some stuff we did earlier. One thing is writing answers to tangent planes rather than tangent lines. So if you have a equation with two independent variables, like say x, y, and the third variable is your dependent variable, say z, you're basically defining some surface defined over your xy or portions of your xy plane, and your z is the dependent variable depending on which xy you're at. So that's going to create a surface, two-dimensional. It actually has three-dimensional characteristics to it, but yeah, it's a two-dimensional surface with bends and folds and that kind of stuff in it, like is pictured here. Let me go on and blow this up. So if it is a surface, then if you had a curve you talk about the slope of the tangent line, the line tangent to that curve at some particular point. So if you have a surface up there, then you can talk about the plane that's perpendicular to that surface, okay? And this will go back to dealing with your first derivatives, partial derivatives now. They must be on that plane, okay? Now, before we go too much with that, though, the concept of tangent plane, we need sort of a definition or description of what we call local linearity, okay? Now, here is get this. Okay. I'll zoom in on this. Well, I thought I was. Oh, there it is. Okay. Okay. Now, sorry to do this, but I think I'm going to have to take a quick break just to step out into someplace that's a little bit warmer and possibly get me clear my head a little bit. So I'm going to pause this right now. All right, sorry about that. So cold in the room, my head is clogging up, so I had to go clear that out. Now, I didn't have anything hot to drink in my office, but I got something that wasn't super cold, but still it hasn't helped much. But anyway, here's the concept of local linearity. This looks like a wrinkled piece of paper, right? And the thing is, how can we talk about or classify that surface? Well, one way is basically you're looking at domains, okay? And you're looking at this in a sense of how does this surface look if you zoom in on your domains a little bit. Now, from a surface, from first picture here, this first indicator here, that looks really wrinkled, and it doesn't look like that is what we would call locally linear at all. But let's just take that point P and focus in on a very small portion of the domain, not the whole sheet of paper, but a very small portion, and that's that little circle that they have there around this part of the P, right here. I don't know if that the hand shows up on your thing, but you see there's a grid there reflecting what the XY is below here, and this is the Z part, and there's that part. Well, let's just blow up on that. Now, why they made this look rectilinear, I don't know who. I guess for the grid purposes. But if you blew up this part and expanded it out here, then you see it's getting a little bit flatter looking, you might say. And you take another small sample of that close to the P, okay, and you blow it up, and now you're getting something that's almost flat. Not quite, but it's almost flat. That's what we mean by local linearity. Now, there's some curves, and we'll run into some of these, I'm pretty sure, or maybe we have already, I don't recall, that are angled and jagged, and no matter how much you zoom in on it, there's always going to be a crease or a peak there, and they may not have local linear area such as this. But this is one that is. The graph looks flatter and flatter as we zoom in on the point P. Okay? Now, let's go back to, and frankly, if you look at figure 1 and figure 3 in your text, that's figure 2, there almost seems to be very little difference there, but they've drawn a couple of extra things there. But before we get to that, let's look at this operator they call a linear, I guess a linearity operator, okay? You're looking at the operator on XY, linear operator there. It's f of AB, so pick a point AB. F of AB is going to be that point, so like that center P that we had, plus your partial of f with respect to x, evaluated AP, B, times x minus a. It's kind of like the slope in the x direction, f sub x, first derivative, partial derivative here, but it's like the slope in the x direction, times x minus a. That would give you which way you're going in the x direction along the x-axis from point A, plus f sub y of AB times y minus b. This is your, and this is theorem, no, I'm sorry. Okay. Again, now this is the two editions of the book. These are a little bit different. Basically, this thing they're calling L of xy now is the equation for the tangent plane. Only make L of xy, make that z, is equal to f of AB plus f sub x AB times x minus a plus f sub y AB times y minus b. That's exactly that tangent plane. Okay? Now, now we go back to the figure we were talking about. This goes back to figure 3 at the bottom of the page, page 767. I think I can get all this on one slide. Let's see if I can. Okay? Now, this figure 3 is the A part. Figure 3 in your book is this figure 3A in this one, in the slide set. It shows that surface, very similar to the one we had before, and it's showing the surface and a point, and at that point, it's showing the tangent plane at that point. Okay? Now, goodness, I'm cold. That point is AB. A on the x-axis, coming out, A units on the x-axis, B units on the y-axis, and then you go up till you hit the plane, and that's the point F of AB. Your Z is F of AB. Okay? Now, on that surface, okay? Now, that point there on that surface where the plane touches the surface that we're dealing with, that point is AB, F of AB. Okay? Now, if that linearity operator, you might say, which is basically going to be our definition of your equation of the tangent plane, that's what Z is here. And at that point, AB, F of AB, then your, if you hold the y constant and you do your partial of f with respect to x, of course y is constant there, you're going to get this line here, okay, at that point B, and that's going to be based on your partial of f with respect to x at that point. Partial of f with respect to y at that point, at the P again, when you hold x constant at A, then that gives you this here. So those are the two lines there that are going to define your tangent plane. The plane that contains those two lines is your tangent plane. Now they talk in this the figure here about the error, the difference between those, your text doesn't focus on that quite as much. Well, it does too. This is basically what we're looking at here is figure 4 also. So here's that error and the, I don't want to say error function because there is a function named that, but the function we use to measure that error. Well, sorry, I should go back to zoom in here. And here's that function that does that. Here is your surface, that z is equal to f of xy, and then the plane here is that z is that linear function, linearization function that we were just talking about. That's this planar surface. Now, as long as your point is not too far from AB, your xy down here is not too far from AB, it gives you a reasonable approximation. The closer you are to point P, the more precise that estimate is. However, too far away, and it can get quite distant. This is the error between that, and they call it an absolute value here because your surface could be coming down from above and your tangent plane is below it rather than above it like this shows, whichever way it is, depending on which way that function is curving, the surface is curving. So they do the absolute value of that error, the E there, and that's the difference between your f of xy and your L of xy, f being the original function you had, and L being the equation of the tangent plane. So what is the difference of those? That's your E of xy. Okay? We're dealing with the absolute value of that. So, that gives you kind of a picture of what we're going to be doing and why we're going to be doing it. To me, it's a pretty vague picture. It's just talking about a lot of stuff. Here is the definition of differentiability when you have more than one independent variable, okay, which is our case here. All right. Assume the f of xy is defined on some disk D containing the point AB. That point AB is the one we were calling P before. And that the partial of f with respect to x at that point and the partial of f with respect to y at that point both exist. Okay, this doesn't work if they don't. If you have some infinity coming in or some place where the partial is just not defined, that would be we have that disk there, okay, so that those things are true. Now, f of xy is differentiable. Here's the requirement. That f of xy has to be differentiable at AB, okay? That's why we said that f sub x at AB and f sub y at AB have to exist. If it is locally linear, okay? In other words, if you zoom in on it more and more and more, you finally get something that looks pretty much like a flat surface. I mean, think about this too. This, wish I had thought of this sooner, but if I go to write on this, it's going to try to remember to come once I'm no longer reading this, okay? And what that means to be locally linear is that f of xy is equal to some the local linearity is if you keep zooming in on it, your surface gets flatter and flatter until it looks almost like a plane. Not exactly. Now, what I was saying is what I want to do is when I get off this slide, make an analogy to a curve, and we'll do that too. Okay, so anyway, that's what we mean. So your f of xy is then your tangent plane at xy, okay, plus that error, the difference, which is the error between those two, where e of xy satisfies this limit. The limit as xy approaches ab of e of xy, that's your error function. It's not the exponential function, that's your error function, whatever it happens to be in this problem. And that okay. All right. So basically this is saying this, I keep wanting to call it an error function. It is a function that describes the error, but the reason I don't want to call it error function, there is a special function in calculus called the error function. This isn't it, okay? But this function that differs the L of xy from the f of xy, that's how much error you've got here. If you take that difference and divide it by the basically it's, I want to call it a magnitude. It has the same form of that, but it's the square root of the difference in x and a squared plus the y and b squared, okay? And the farther they are from the point AB, the further the x and the y are from that, then the greater your error function is, that what I'm calling error function. The tangent plane to the graph and let's see, in this case, the tangent plane to the graph, AB, f of AB, is the plane with the equation z is equal to, and that's what we were talking about before, okay? Well, the earlier slide was calling, I don't remember how, L of xy, yeah. That is exactly it. That's what, and z is equal to that. So that's where that comes from. Now, before I go on, let's go back and just imagine, okay? Let's do a good old curve, okay, in two space. Y is a function of x, okay? Now, if you pick a point here, any point here, okay, there's the point. If you do the tangent line there, notice that the difference between the function and the tangent are extraordinarily small, really close. But then the further out you get, the further off they get. Okay, this would be corresponding to the error function. How much that differs the curve from the tangent point. Okay? Now, expand that to a surface like we had back here, and the tangent plane, and there's your error. It's the difference you have between the two there. Now, how do we define the plane? As we've already sort of hinted, then they are dropping it. We're going to pick it up later. That is related to the partial derivative in the x direction, where y is constant, times x minus a, and the second line is the partial of f with respect to y at the point AB. And that defines a plane, a slope of a line there. and those two lines where they intersect, that contains the plane. All right. Sorry, I've got almost getting hiccups, and it's hard to talk. All right. Theorem 2 here, following shortly from that definition, is criterion for differentiability. Now, that's something that's fairly important here, so let's hit it. If f sub x of xy, that's the partial of f with respect to x at some point xy, and the partial of f with respect to y at that same point xy, if they both exist and are continuous on some open disk D, then f of xy is said to be differentiable on D. Okay? Now that, I swear, almost sounds circular to me. If the first partials exist and are continuous on an open disk, then that function is said to be differentiable on that disk, D. Okay? And again, you think, well, what do we mean by that? Well, if you're locally linear, those just mean your tangent lines. And if the tangent line exists, it's differentiable, almost the same kind of logic we used before. So here's a figure for example 1, okay? And this is, I'm glad they've drawn this because I would have a terrible time drawing this figure, okay? Can't get that to go away. All right. Man, there's a lot of noise outside today. Of course, maybe there is every day. I just don't have my windows open when I'm at work. All right. Over the weekend, it transitioned from being pretty chilly like it was last week to much warmer over the weekend. And I went through a series of, well, no longer need a t-shirt, no longer, and then so today I came in without a t-shirt thinking, yeah, it's nice and warm. That's outside. Here in the building, it's way too cold for this. I mean, there's no reason in November to have air conditioning on at this level. If we just had ambient air circulating, this would feel great, but we don't. They're really chilling here. I wish they didn't. So there's figure 5 in your text. It's figure 4 on the slide set here, but it's figure 5 in your text. And this shows example 1. It says, shows that f of x equals 5x plus 4y squared is differentiable, and find the equation of the tangent plane at the point 2, 1. So to show that it's differentiable, according to our last thing, it's differentiable if both of those first partial derivatives exist. So let's do the partial derivatives. F sub x at any xy would be 5, and f sub y at any xy would be, I can't read my writing, 8y I think it is. Okay, to write on the slide, it's so small now. Probably what you see looks bigger, but my screen is a small screen, and then it's a smaller screen within that. I might try something here. This is a little bit better. And I hope you can see that. I don't know if it makes any difference to you, but it sure helps here. Okay, so here is your f of f sub y. F sub x of xy is 5, f sub y of xy is 8y. Okay? Now, it says, and that's, both of these exist, they're continuous. Okay? So therefore, if both of these exist, are continuous on some open disk, this open disk can be from minus infinity to positive infinity. It's everywhere. Then f of xy is differentiable. So we've proven the first, because both of these functions, constant function and the linear function, they exist and are continuous on any open disk you have throughout both infinities. Okay, so we've shown they're differentiable. Now it says find the equation of the tangent plane at AB is equal to 2, 1. So at this point right here, AB is equal to 2, 1. Okay? Well, let's start with our function here, and f of 2, 1 is going to be 5 times 2 plus 4 times 1 squared is 1, and that's going to be 10 plus 4 is equal to 14. So that's where that 14 comes from. Okay? That's the z value when x is 2, y is 1. Those are independent variables, x and y. The z is dependent on the x and y. Okay. Find the equation of the tangent plane at that point AB. Well, if you look above, the equation of the tangent plane is z is equal to f of AB, which is, I'll write it down, f of AB plus f sub x at AB times x minus a plus f sub y at AB times y minus b, x minus b. Okay. Goodness, that came out ugly, didn't it? Okay. I don't know why this eraser doesn't seem to be working well. Okay, I can't get my pen back now. Yeah, this is so frustrating. Usually the right click will bring up the options, but it's not bringing up the options anymore. Where did I get that? I went to hide presenter view so it would be easier to operate, and now the pen's not. Man, what a pain in the neck this is. Oh, my cursor's not. For some reason, the cursor is hung up. Let me try Control Alt Delete and see if. Everything seems to be all right. Let's turn that off. Okay. Well, at least I got my cursor back. Well, I thought I did. No, I don't. I don't know what's going on, folks. Okay. I know I don't want to end this. sheet again. I don't think any of these have anything to do with it. It just is not responding. I think Dr. Bryant said this computer just didn't work well on this. And maybe if I end power, but I want some control back again. And I see no way of getting it. I guess I'm going to have to end the recording.